Okay, welcome to this course on network information theory. This is a slightly advanced course, and it's a follow-up course to your set of information theory courses. I'll assume that you've at least taken one of these courses, either information theory or information sciences. And so let me just share my screen. Right, so we have a course web page which hopefully has been shared with you, and all our discussion will happen on Piazza. So if you haven't received the invite for Piazza, just let me know. I'll share the invite. I'll assume that you have taken either the information sciences or the information theory course. That is more or less sufficient. Although I will cover most of the topics, will refresh some of the topics in this course, but we'll go through it a little quickly. So it would have helped if you've already seen that previously. So I'll assume that you're comfortable with probability and random processes because most of this course will be based on that, and it's helpful, but not mandatory if you've taken either the source coding or the channel coding course. But again, we'll cover most of that in this course anyhow. And so the assessment, it's still tentative. Ultimately, it will depend on how many people attend the course, and we'll see as the course goes. But generally, there'll be a part of your grade will be determined by you attending lectures regularly. And in this course, we'll also try to experiment with scribing lecture notes. So each of you will have to prepare lecture notes for a class and then submit it. So, so maybe one person will scribe a lecture note per class, and so by the end of the course, we'll have a nice set of lecture notes contributed by you, and that will also help you get familiar and get more comfortable with the subject. At the same time, it's also part of the grade. And there may or may not be quizzes, but there'll certainly be some homeworks, and there'll be a final paper presentation or a project presentation, and more details about the final project presentation or paper presentation. That I'll share more details about that. I'll share a list of suggested topics, but you're completely free to choose any topic or paper related to this course. So that's about it. And this course will be taught by myself and Dr. Lakshmi Prasad. Dr. Lakshmi Prasad is also here in this is here with us today. And so I will be teaching the first 2/3 of this course. So segments 1 through 4, and Dr. Lakshmi Prasad will be teaching segments 5 and 6. Currently we are going to have live classes in slot R, but again, so maybe we'll share an email with all of you and try to find out if the slot is okay for everyone, or if we need to have a slight change in slots. Anyway, we'll share a poll with you, and then we can finalize on the exact slot. But tentatively, this is the slot that we will stick to. So as I mentioned, this is sort of a second course in information theory and is about multi-user systems. The list of textbook and the references are listed over here. This is only a small list, but primarily we'll be following this book, Network Information Theory by Abbas Al-Gamal and Young Han Kim. There are also a couple of copies in the library if you're on campus, but otherwise, yeah, I guess you'll find an online copy. And so we'll start off gently. I'll assume we'll start with the basics. I'll first motivate the course, and then we'll start with some mathematical preliminaries. Now, all of this is typically covered in your high school or undergrad. You would have seen some of this previously, but then perhaps not in the amount of rigor that is needed. Or in any case, it's always a good idea to refresh some of these concepts because they will be important in the rest of the course. So once we finish these mathematical preliminaries, some basic analysis, convexity, and probability, we'll start with some basics of information theory. Now, again, you've seen some of these topics in your information theory or information sciences course, but many of these topics will also be new to you because so we'll introduce some very powerful tools which are useful not just in information theory but also in statistical inference or theoretical computer science. So these are some very interesting tools, and we'll see all of these. And then, so this is, you can consider this as sort of slightly more advanced topics in like information theory. But then we'll then, once we talk about point-to-point communication in discrete memoryless channels and source coding, we'll then go to actual multi-user systems, which is really the core of this course. So in this course, we'll basically see two kinds of multi-user channels, which form basic building blocks of larger communication systems, and we will study these in some detail. So I'll cover the topics up till multiple access channels, and then the rest will be covered by Dr. Lakshmi Prasad. Now, this was just a sort of very high-level overview of this course. But anyway, we'll start gently. We'll start with the basics. I'll assume that you know some amount of probability and information theory, but then we will start with everything. We'll start from scratch. All right. So those were the logistics. If you have any questions related to the logistics, please let me know. Also, throughout the course, just feel free to interrupt me in between. I want to make sure that this class is as interactive as possible, and don't consider this like a regular course. Your focus should not be on just writing exams and securing a grade, but it should really be in learning the material over here. So again, just feel free to just unmute yourself and ask me questions in between. You can also type them in the chat box, but it's preferred that you speak because it's always interactive communication is always better, and also I may not be monitoring the chat window all the time. So any questions related to the logistics or time slot or anything else? Okay, so if not, then let's proceed. So to begin with, this course, as I mentioned, is a follow-up to the information sciences or information theory course. And this is a very useful course if you're working on projects or research on information theory or even distributed systems, wireless communications, wireless networks, or physical layer security. So whenever you're working on these problems, you'll always encounter terms and concepts like rate regions or achievable rates. And this course is going to basically introduce you to all of these concepts, and we'll see this formally. So you should take this course if you plan to work on these areas. But also if you're curious to know more about information theory, or even otherwise, if you just like math and like to see interesting problems, then this is a rich source of problems. So this will be a mathematical course. We will see a lot of theorems and proofs. And also the hope is that you also develop the rigor to formally analyze a system. And but the end goal is always to understand and gain intuition for practical wireless systems and networks. So how do you communicate reliably in the presence of interference and noise? Right. So we'll all start from scratch. But at least when we do the initial part, I'll go a little quickly. I'll skip some of the steps of the proof, and I'll expect you to fill in the details. So it's very important that you interact in class and also follow up on the material that is shared with you. And you will have to sort of fill in the gaps if you really want to understand the subject. So it's not enough if you're passive. You should also be actively engaging in the material. All right. So let's start off with the motivation for this course. So if you look at a general communication system, let's say a 5G cellular communication system, then what does it look like? It consists of multiple users who are all trying to communicate with each other. So when you let's say decide to call your friend, or when you decide to say visit a website using your cell phone, then what really happens in the background? So a cellular communication system would consist of a very large number of users, such as ourselves. Each of us have our cell phones, which talk to a base station, right? These base stations, and in the background, the base stations are not directly connected to each other. There are a lot of other entities sitting in the background. So typically, if you look at, say, the 5G communication network, then it consists of base stations which communicate with what is called a backhaul network. And these consist of devices which are either typically connected through fiber optic links, or it could be just normal wired links, or even wireless links. So the link between us and the base station, this is of course wireless, but the links over here are typically wired, sometimes fiber optic, and this backhaul network generally communicates with the core network, which decides, okay, where this information has to be sent. Let's say you're calling your friend somewhere in another state or in another city, then it goes from the base station to the backhaul network to the core network, which decides where this needs to go. If you want to visit the website, then from the core network it goes to the internet, and it downloads a particular page and it's sent back to you. Right? Or if you are trying to communicate with someone else, then it goes from the backhaul network to the core network, and then back to some other base station, and there'll be a user sitting over there who will be talking to you. Right? So overall, there are a very large number of users who are all trying to communicate with each other, and these links are not reliable. They're noisy, and if you look at, say, a city like Hyderabad or Bangalore or New York, you have a very large number of people connecting to a single base station. Right? You can have tens or hundreds of people communicating to a single base station, and that means that there's a lot of interference. Right? The signal that is sent by you, so you are sending some signals on a particular frequency at a particular time, but then there's also another user who is sending his or her signals on the same frequency at the same time, and somehow we have advanced enough communication systems that despite the amount of interference and noise that we have today, communication still happens very reliably. You can download at several megabits or megabytes per second, and you can communicate almost noise free with someone else, right? And so in this course, we'll see the basic principles that are involved in designing such communication systems. And, uh, and although we will not explicitly look at algorithms which achieve this, we will still see the basic principles, and more importantly, we'll see what the fundamental limits are. Right? So if you have 10 users communicating to a single base station, and each of us has a certain power budget, then what is the maximum rate? What is the maximum throughput at which we can communicate with the base station uh, uh, at the same time? All right. So to start with, we need in information theory, we always start with a model for the communication system, right? So when even in our information sciences or information theory course, when we wanted to study the reliable communication between two parties, there's a sender and there's a receiver. That's the simplest communication system that you can think of. So you have a sender who wants to send something to a receiver, and there's a noisy medium in between, right? And we want to communicate essentially error-free in presence of this noisy medium, like through the noisy medium, right? So what Claude Shannon in 1940 in the 1940s, so the way he modeled the communication system is that you have a source who's producing some bits of information. Let's say that the source is producing, I want to send k bits to my friend who's sitting somewhere else through a noisy medium, right? So how do we first? So the first question is, how do you model the noisy medium, and how do you model the source? There are two objects over here. One, which is the source, right? And you have a channel. And the goal is to communicate these bits which are generated by a source through a channel. So the idea that Shannon had was, okay, let us model the source as a random process. So let us assume that the source produces k bits of information. And he assumed that, okay, this is a random source, so it produces k uniform bits. And this needs to be sent through a channel, and the imperfections in the channel are modeled as, so the channel is also modeled as a random system, and so basically the output is going to be a random process which is dependent on the input to the channel. So you can basically model the channel as a black box which takes some input signal and outputs some other signal, and the output signal is a random signal which depends, whose distribution depends on the input. So the channel is basically a conditional distribution, and a very simple model that we used for the channel was, so we assume that this is a discrete memoryless channel, which means that given x1, x2 up to xn, the output, each component of the output is conditionally independent of all the others given the current input. So basically, the channel is modeled as through a single conditional probability density function or a conditional probability mass function, which we call the transition probability. And the transition probability basically determines what the channel is, right? And the goal is to design an algorithm, an encoder and a decoder, such that we can have essentially noise-free communication from the source to the destination. Right? So this is a single point-to-point communication system where you have a single sender and a single receiver. right? Now, when you have a multi-user system, you have multiple senders, you have multiple receivers, and you can also have some other users or devices or entities which are neither sources or destinations, but operate something like a relay. Their only goal is to help in communication. Right? So you can think of a more complicated system where you have multiple users who communicate through a complicated channel to some other set of users, and you have multiple such hops, right? So, for example, in the example over here, you could view this as multiple users communicating through a single channel to maybe one base station or multiple base stations, and that communicates with some backhaul network and so on, right? But the system can be a lot more complicated in the sense that this need not be just unidirectional communication. There could be bidirectional communication. Communication could be interactive and so on. So these are, so if you think about it, about the general problem of communication in multi-user systems, it seems as though it can get quite complicated, right? And what we will do is that we will try to simplify the channel, or we will try to simplify the system and try to analyze some basic building blocks. So it's okay even if you have a really complicated system, but you can always divide the whole complicated system into much simpler blocks. And therefore, in network information theory, we see some very basic systems. So one basic system, so any communication system, any complicated multi-user communication system can be modeled using a graph, right? So you have multiple users, right? Let's say these are users who all communicate with a single base station, and this maybe communicates with a backhaul network, and maybe this communicates with these communicate to a source, to the core network, and so on, right? So you can represent your communication system as a graph where you have an edge bit. So each of these vertices represent a particular user in the system, and there's a link, or there's an edge between two users if there is some kind of a channel between the two. Right. So more generally, you can have, so a general communication network could be something really complicated, but the goal is to always simplify. Let's look at the most basic building blocks, right? So one basic building block is the so-called multiple access channel, which we will study, and that consists of multiple users trying to talk to, so you have multiple sources, maybe n sources, who are trying to communicate to a single destination. So that is one basic system. And the other basic system is you have a single source who's trying to communicate to multiple destinations. All right. So the first is what we will call a multiple access channel, which we'll study in detail in the course. And the second is what we call a broadcast channel, and this is also something that we will study in detail. So a multiple access channel is basically, you have a lot of people who are trying to talk to a single person, right? So think of, so both of these are essentially components of a cellular system. So you have multiple cell phones which are communicating to a single base station, right? And that, it's after all two-way communication. The cell phones send some signals to the base station, and the base station also sends some signals to the users or the cell phones, right? So when cell phones communicate to multiple cell phones communicate to a single base station, then this is essentially a multiple access channel. So as the name suggests, it's multiple access. You have multiple people who are trying to access the same channel, and when the base station is trying to communicate to these users, it's basically a broadcast channel where a single source is trying to communicate to multiple destinations. So you have different messages to send to different destinations, but you're trying to use the same channel, right? And effectively, what we have over here when I am talking to you is basically a broadcast channel, although it's hard to say whether it is error free or not, right? So any questions so far? Okay, so here's a question to all of you. Are wired channels multiple access channels or broadcast channels, or are they just point-to-point communication channels? Yes, anyone?
So can you repeat the question?
So if you have a wired channel, right? So let's say you're using your Ethernet cable to communicate to the internet, right? So is this a point-to-point channel, or so suppose you wanted to model this communication system. So would you model it as a multiple access channel or a broadcast channel, or how would you model it?
Okay, point to point.
Right? Yeah, so it's something like a point-to-point channel. So the key factor or the key property which distinguishes multi-user wireless channels to wired channels is that you have multiple users who are competing for the same resource, right? And that is really the challenge behind multi-user communication or network information theory in general. And that is what we will try to understand. Okay, so let's recall some basic information theory. So let's see. So what does so again, suppose we have a point-to-point channel. We have a single source, a single destination. The goal is to communicate k bits as reliably as possible through a channel which is modeled using a channel transition probability Py given x. Okay, and recall that so basically a channel code or a channel coding scheme or an error correcting code consists of two things, and an encoding algorithm or an encoder, and a decoding algorithm or a decoder. Right? The encoder takes k bits, k information bits or k message bits, and outputs a code word which is of length n. So the assumption is that you have k bits of information which you want to send through the channel. Maybe there are n time slots or n time instants across which you can communicate. So the total duration of communication is n time slots or n instants, and the output, the channel outputs, given that suppose you give xn as input to the channel, the output of the channel is some yn, and the decoder takes the received signal or yn as the input and outputs k bits, which are estimates of the message. Right, so this is the message, And the encoder takes k message bits and outputs a code word of length n. The output of the channel is some vector by n, and the decoder outputs an estimate, which we call mk hat. So for example, these message bits. So we have some message bits, and these are converted to say n code word bits, or this could be also you could do joint encoding and modulation. So the output alphabet, or sorry, the channel is some system which could take a set of n symbols. Maybe these are QAM symbols, right? Or they could be, depending on what kind of a modulation scheme you use, or depending on what kind of a channel you have a set of, say, n real numbers. Maybe you're using BPSK, so it will be a sequence of +1, -1, -1, +1, and so on. And these are transmitted through the channel, and the output is, this is corrupted by noise, so the output could look like 0.1, 0.3, and so on. So you get a bunch of n real numbers. And given this received vector, the decoder tries to make an estimate as to what the actual message was. Right? And to quantify the performance of any such channel coding scheme, we look at two parameters. One is the rate, which is k over n, the number of information bits that you can send per channel use or per time instant. And the other is the probability of error. So what is the probability that the message is decoded incorrectly? And the goal is to design these encoders and decoders such that the rate is as large as possible. At the same time, the probability of error is as small as possible. All right? And Shannon showed that it's possible to construct encoders and decoders, or it's possible to construct channel codes such that for really large n, so if you assume that you're allowed a very large number of channel users, or you're allowed to communicate for a very long period of time, then the number of bits of information that you can send per channel use or per time instant can be as large as mutual information. So in particular, this is true for any input distribution. So it's equal to the capacity, which is the maximum overall possible input distributions of the mutual information between X and Y. Right? At the same time, the encoder and decoder must, of course, guarantee reliable communication, which means that the probability of error can be, for very large n, can be made arbitrarily small. So in the limit, the probability of error is equal to 0. All right. So this is for just for point-to-point communication systems. Right? And you've seen all of this in your information sciences or information theory course, or in your channel coding course. Right? So the question is, okay, so now what is new about multi-user systems, and what can you do? So is it not enough to just consider the system as multiple single-user channels? Can you not convert your multi-user channel into multiple point-to-point communication system links? And so we'll see that in some detail. And so let's look at this simple communication system as an example. So the channel is basically what I have over here. So this is what I call a two-user Gaussian MAC. So let's see how studying network information theory can help and what it offers more than what you would see in a typical information theory course. Okay, so let's see what happens. So suppose I have the following system where I have two users or two sources, let's say two cell phones who are trying to send messages to a base station. Okay, so I have two senders and one receiver. I have two senders and one receiver. Okay, so sender 1 wants to transmit K1 bits of information and sender 2 wants to send K2 bits of information. Okay, and the goal of the receiver is to recover both the messages, so K1 plus K2 bits of information. Okay, so what can you do? So sender 1 basically converts. So in order to so the system or the channel between the two senders to the receiver is basically the following, what I have over here. So if I send a vector of length n, so at any particular time instant, if sender 1 sends xi and sender 2 sends yi, then the receiver gets xi plus yi plus some noise. Okay, and the goal of the decoder or the goal of the receiver is to recover the two message signals in such a channel. Okay, so this is the communication system. So think of it as though you have two cell phones trying to talk to a base station, and you have, say, just line of sight from the say both of them are very close to the base station. Okay, so what is received by the signal received by the base station is equal to the sum of the signals transmitted by the two cell phones plus some noise. Okay, we'll assume that the noise is Gaussian. With zero mean and let's say variance sigma star. Okay. So any questions at this point? Is this system clear? Any questions?
Will it be on the same resource or it doesn't matter, sir?
No, it's on the same resource. Right now, this is just the model, right? They're using the same frequencies. They're trying to communicate at the same time.
Okay, sir.
Okay, so you have some resource. Let's say that both senders are using the same bandwidth. Maybe they're operating at whatever 2.4 gigahertz, and both of them are trying to communicate at the same time. But that's again. So the model is the following: that you are allowed to, each user is allowed to send in n time instants, whatever that means, is allowed n uses of the channel, and in each use he is allowed to send one real number, right? And the receiver sees the sum corrupted by some noise. In addition, typically there are power constraints, so you want to ensure that summation I going from 1 to n xi square is less than or equal to some n times P1 and summation I going from 1 to n yi square is less than or equal to some np. So these are power budgets. Both users have a small or finite battery, and the goal is to communicate reliably to the channel, to the receiver. Okay, so the goal is to design a system so that you can transmit the maximum number of information bits per channel use. Basically, n channel uses. You want to ensure that both the number of bits that you can transmit, the number of useful information that you can transmit is as large as possible. And the probability of error, so the communication has to be reliable, so the probability of error has to be as small as possible. Okay, so again, I'm not going to be very rigorous with this in this class. Again, we just try to build some intuition for how do we model communication systems and how do we analyze communication systems. Right? So you have two users who are trying to communicate to a base station, and this is R1 and R2. Okay, so suppose you had, know that all that you know is just what you studied in your information theory course. How would you design a system? So how do you think you could communicate? So you know that if you have a point-to-point communication link, so if you have a single transmitter and a single receiver, then you know at what rate you can communicate, right? It's equal to this quantity, which is the channel capacity, right? But now you have two users who are trying to communicate to a single destination, and they're basically using the same set of resources, right? So then, can you suggest something? What would be the first thing you could think of? So you know how to mitigate the effects of noise, right? So if it was just Zi equal to Xi plus Wi, you know what is, you know, you already have a scheme. You know that there are channel codes which allow you to get to channel capacity, and you know what the channel capacity is, right? So in this kind of a channel, so just the AWGN channel, what is the maximum rate at which you can communicate? If you have a single point-to-point communication channel, which is basically just this AWGN channel, Zn equal to Xn plus Wn, what is the maximum rate of reliable communication? Do you recall from your information theory course? Correct. So what is the channel capacity for the AWGN channel? Assuming that the noise has variance sigma square and the transmitter has a power constraint of P. Correct. So it's not log half plus, so it's half log 1 plus P by sigma square. All right. So it's possible to transmit NC bits, NC information bits in N channel uses, and at the same time ensure that the probability of error is close to 0 as long as N is sufficiently large. Okay, and so you know what is the best rate that you can achieve if you had a single point-to-point communication link. All right, but now we have two users who are competing for the same resource, right? So if this second user were not present, then you could just have for the first user use a channel code and then communicate directly to the base station, right? But no encoder to the second user also wants to communicate. So what do you think you can do? Any suggestions? So think about it in practice. Let us say that two people just want to talk, speak to one particular person. Okay. Obviously, if both of them try to talk at the same time, the person who's receiving or the person who's listening can't really understand what they're saying, right? So now, what do you think we should do?
Only one can use channel at a time.
Scheduling.
A scheduling kind of.
Correct. Exactly. Good. So what we can do is we'll say, okay, so user one is going to communicate or is going to talk for some time, and then he's going to remain silent. So when user one is talking, second user remains silent, and when the second user is talking, the first user remains silent. Right? So that's a good strategy. So what we do is what I call time division multiplexing or time division duplexing. Right. So user one speaks. So user one speaks for, let's say, alpha n channel users, and user two speaks in the remaining 1 minus alpha times n channel users. Right. So user one is allowed to speak for alpha n channel users. So how many bits of useful information can user one send?
Alpha and C.
Correct. So alpha nc bits can be sent, and so what is the and the rest? So basically, in n channel users, user one can send only alpha nc bits, right? So there are a total of n channel users, but now user one is only sending alpha nc bits. Okay, and user two is now going to send 1 minus alpha nc bits, right? So let's call this C1 and C2. Let's keep it simple. Let's see, alpha nc bits. Okay, so what is the rate of communication of user one?
K by alpha n c.
Right, so it's alpha c, right? So it's k by n, so it's alpha nc by n, which is alpha c. So and similarly, what is R2? The rate at which the second user is talking. Correct. So it's 1 minus alpha times c.
C.
Okay, great. So now we have all we knew. So before approaching this problem, all we knew was point-to-point communication, right? So we know very well how to communicate as long as there is one sender and one receiver. Now that we have two senders and one receiver, we have an algorithm, right? Or we have a scheme, and this performs. So let's see how this performs. Okay, so how do we measure the performance? Let me draw a plot. Okay, so R1 is the rate at which user 1 can transmit, and R2 is the rate at which user 2 can reliably communicate to the receiver, right? So now if we use this time division multiplexing scheme, then I know that R1 is alpha times C and R2 is 1 minus alpha times C. Correct. So this is the rate at which you can operate, right? And where alpha is some parameter which you can vary. Right? So C you can anyway not communicate at a rate higher than capacity. Correct. So here C is simply half log 1 plus p by sigma square. So this is fixed. This is completely determined by the channel. This is completely determined by the system. Alpha, on the other hand, is up to us. So we can play around with alpha and therefore allocate resources between the two users. So if we increase alpha, then user 1 gets a higher portion, higher rate. So basically he's getting more resources. If I decrease alpha, then user 2 is getting more resources. Okay, so what does this plot look like? So you have R1 equal to alpha C. So basically, this is the maximum rate at which you can communicate, right? So any rate below this is achievable. So R1 is less than or equal to alpha C and R2 is less than or equal to 1 minus alpha C. So any rate satisfying these constraints can be achieved. We know how to design a communication system such that we can operate at these rates. Correct? So what does this region look like? So you can take maybe a few seconds to think about it. So what would this region look like?
Line passing through 0, C and C, 0.
Yeah, so sorry, okay, so maybe Shiva, Moni first.
Line passing through 0, C and C, 0.
Okay, Suman?
So it will be like a square, like R1 will have a straight line at alpha C, and R2 has a line and 1 minus alpha into C. Then these two lines will intersect at alpha C into 1 minus alpha C, and then anything.
So sorry, your voice is not. I can't hear very clearly. There seems to be some noise.
What I'm saying is it clear now?
It's pretty much the same. Maybe you can say it a little slowly.
Okay. What I'm saying is, so it will be a square. So like alpha R1 we have a straight line at alpha C, and R2 we have a straight line at 1 minus alpha into C. These two lines will intersect at alpha C into 1 minus and 1 minus alpha into C. And any rate which is both less than these points, that will be achievable, and otherwise it's not achievable.
So what is the shape?
Square.
Okay, that's not actually true. So it's really going to be so of course, if you look at just R1 equal to alpha C, R2 equal to 1 minus alpha C, that will just be a straight line between C and C. So it will be this straight line. So any point on this straight line, so this is basically just a convex combination. So this will be alpha C comma 1 minus alpha C, depending on alpha. right? So as you vary alpha, you'll be basically moving along this line. So R1 less than or equal to alpha C, R2 less than or equal to 1 minus alpha C is basically going to be this region over here. So it is essentially this triangular region. So any rate in this triangular region can be achieved. So so now we know how to design a communication scheme such that we can operate at any point in this triangular region. Okay, and now we've just done this with with no extra knowledge. All we used was plain channel coding theorem, nothing more. Okay, so before we proceed, any questions? Is this part clear? Okay. So this is what we would get with just time division multiplexing. Now, obviously, the question is, can we do better? Yeah. So the question is, can we do better? And it turns out that in fact we can. So as we'll see later in this course, we can achieve not just this triangular region, the actual capacity region, or the set of all achievable rate pairs is not going to look like a triangle, it's going to look like a pentagon. So in fact, it will look something like this. I apologize for my bad drawing, but it's going to look like this pentagon over here. So any rate in this entire region is going to be achievable. Okay, and the idea behind this is in fact quite simple. I can in fact just directly describe you the scheme which goes from the triangle to the pentagon. And the idea is basically the following. So now you have two users sending to the same receiver. Let us say that I want to achieve some point over here. So what do I do? So one scheme is the following. So first, the decoder. So both user 1 and user 2 simultaneously transmit to the receiver. Decoder first decodes user 1's signal. Okay, so basically you have Z, which is equal to user 1 signal plus user 2 signal plus noise, right? And in doing so, in order to decode user 1 signal, it will assume that this entire part is noise. Okay, so let's treat this as noise. It's of course it's not Gaussian, but anyway, let's ignore that little fact for now. So you'll treat that entire part as noise, and you'll try to decode xn. So what is the maximum rate at which you can communicate? So if I want to recover xn from xn plus, let me call this w tilde n. So from xn plus w tilde n, what is the capacity for this channel? Let's assume that w tilde n is Gaussian for now. What is the power of w tilde? So what is the variance?
It should be less than x for decoding process.
Yes, but more concretely, so you know that w has variance sigma square, or Wi has variance sigma square, and Yn has a power constraint of P. Correct? So what will be the variance of W tilde?
It will be power of y plus sigma square, like the maximum power of y plus sigma square.
So, sir, we can say like the P of one, the P of x1 by P of y1 plus sigma square should be greater than 1 kind of thing. Combined, this should be less than.
Sure. So let's not even go to that point yet. But yeah. So basically, the power of or the variance of W tilde n or W tilde I, assuming that Y is Gaussian, this is just going to be P plus sigma square. Right? So therefore, it's possible to design a community, and the power of X is P. Right? So just from Shannon's channel coding theorem, you know that it is possible to communicate at a rate half log 1 plus
P by P plus sigma square.
correct. So it's P by P plus sigma square. Okay, great. So I know that I can communicate. So I can recover user 1 signal as long as user 1 is operating at a rate half log 1 plus P by P plus sigma square. Okay, good. So now that you've decoded the user 1 signal, the decoder will remove that component out. Right? So it gets some estimate xn hat, right, and then removes it from Zn. Okay, so I'll have a Zn bar, which is Zn minus xn hat. Correct. So assuming that xn has been decoded correctly, right? So this is going to be just Yn plus Wn. Now this is just a point to point. This is just an AWGN channel. Correct. Of course, assuming that modulo all of these things. I made many small assumptions over here, but just to give you an idea. Right? So assuming that all of these things go through, you effectively have a channel Yn plus Wn. Correct? And Yn has power P, and Wn is again noise with variance sigma square. Correct? So at what rate can user 2 communicate?
P by sigma square.
Correct. So it's just half log 1 plus P by sigma square.
Sir, one question is, so
Yes.
the first step will be working provided W hat of n is Gaussian, right?
Sorry, your voice is not audible. Can you?
So I'm saying that W. So the first step will be working provided W hat n is Gaussian, right?
W tilde n is Gaussian, yes. So that's an assumption I made, but then it turns out that even if it is not Gaussian, so in fact, as long as it is IID, you can achieve any rate below half log 1 plus P over P plus sigma square.
Okay, sir.
So basically, if as long as you have any additive channel Zn equal to xn plus say W bar n, where W bar n is IID, as long as it is IID and the variance of Wi is say n, and the power of x is p, you can always achieve a rate of half log 1 plus P over N. So in fact, the capacity will be larger than half log 1 plus P over N if W is not Gaussian. So in some sense, Gaussian noise is the worst case noise.
Okay, sir. Okay.
But anyway, I mean, again, I'm making a lot of, I'm being very loose in many of my statements. Of course, W tilde N is not going to be IAD. But again, I'm just trying to give you the idea. Right? So basically, so now let me recap what the decoder does. So both user 1 and user 2 now communicate at the same time. They're both using the same resources. They're talking at the same time. But what the decoder does is the decoder first assumes that user 2 signal is noise and first tries to decode only user 1 signal. Okay, so both of them are communicating at the same time, but the decoder will first try to decode only user 1 signal. And it can decode it as long as user 1 is operating at a rate of at most half log 1 plus P over P plus sigma square. All right, and then once it has successfully decoded user 1 signal, it removes that component from the received signal and then tries to decode user 2 signal. Okay, and that is possible as long as user 2's rate is less than half log 1 plus P by sigma, which is equal to C. Correct? So basically, now it is possible to communicate at rates equal to half log 1 plus P over P plus sigma square, comma, C. Correct? And this essentially corresponds to the corner point over here. And similarly, just using a symmetric argument, you can achieve a point over here. And now that you know how to achieve these two, any rate can be achieved using this time division multiplexing kind of an approach. But anyway, so this was probably a bit fast, but the only take-home message is that just using these, so if you just do something like plain time division multiplexing, then you will be operating along this black line over here. This is the maximum rate at which you can communicate, or this is the set of rate points that you can achieve. But then if you do something a little more sophisticated, you can do something much better. You can in fact communicate at much higher rates. Okay, and we'll see this in the rest of this course. Okay, and we'll see that this is in fact the best that you can do. So the scheme is pretty simple to describe. So you first decode one user signal and then remove the component of that user signal and then decode the second user signal. So this is what is called successive interference cancellation. And it's something which is very frequently used in communication systems. All right, so basically we'll see that at least for certain parameters or certain powers and certain noise variances, successive interference cancellation is in fact optimal. All right. So any questions?
Sir, in
Yes.
SIC, like there should be difference in channel gain, right? I mean, there should be some difference, isn't it?
Not necessarily, right? So here I've given you a successive interference cancellation scheme, which
Sorry, sir.
so
It's not
not
necessary.
necessarily, yeah.
Okay. And this will be at the cost of probability of error because two
No,
times.
right? So both of them can be, of course, for finite n, of course, the probability of error will now increase. But now, if we're looking at large n, then anyway the overall probability of error is small.
Okay, okay, sir.
Right? So of course, so when I say that successive interference cancellation is optimal, it is optimal in the sense that for sufficiently large n, this is the best rate that you can achieve as long for a given probability of error threshold for sufficiently large n. So again, we'll make this all of this more formal as we go on. Right now, I'm being very loose in all of my statements. So, any questions, particularly from the undergraduates?
Hello, sir.
Yes.
Sir, once more, can you explain how did you improve it, sir?
Okay.
Briefly.
So the first part was fine. The time division multiplexing can achieve that black line. Is that part clear?
That is clear, sir.
That is clear, right? So now the point is, how do we improve upon this? Can we achieve, so the black point would get you maybe some point over here, and we want to do better than this. So what do? So instead of having one user remain silent for some time and only one user talk at any particular time instant, we'll say that both users are going to communicate at the same time. So both of them will simultaneously talk to the receiver, but they're going to talk at different rates. So they're going to use different code books. So user one, and basically the idea is that the decoder will first try to decode. So since both of them are talking simultaneously, it will try to decode them successively. So first try to decode user one signal. So you have xn plus yn plus wn, that is what the channel is. So you first try to decode xn, assuming that yn plus wn is noise. Okay, so it will just ignore. So for now, you'll ignore what user 2 is sending. Right? It will wait for n time instance and then get zn, and then first try to decode xn, ignoring the rest of the components, so assuming that the rest of it is noise. And you can do this. You can, if as long as user 1 is using a good capacity achieving code, which is operating at a rate close to half log 1 plus p over p plus sigma square. Okay, and then now that you have decoded xn, right, you already have zn, right? Zn is something that you have stored. So you get xn. Now you remove the component of xn. You have successfully decoded xn. So you remove that component from the received signal, and then now all that remains is yn plus wn. Right? And then you try to decode yn from yn plus wn, and you can do that as long as your rate is half log 1 plus p over sigma square. So therefore, it is possible to simultaneously talk to the receiver when R1 is half log 1 plus p over p plus sigma square, and R2 is half log 1 plus p over sigma square, which is c. Right? And this point over here, R1, R2, basically corresponds to this. So R2 is half log 1 plus p over sigma square, whereas R1 is half log 1 plus p over p plus sigma square. Right? And a similar argument can be used to achieve this point over here. And similarly, you can achieve these points as well. Is that okay?
Yes, sir. Clear, clear.
Okay, good. Yeah. And anyway, we will come back to this later on. So the only point here is to just give you a flavor of what is to come. Okay. So the point is we'll try to make all of this more formal. So first we will again revisit single user information theory and then get to these points, right? But in order to do this, we will have to study systems and basically the asymptotic behavior of systems, because after all, when we say capacity and rate, we're looking at systems when n is very, very large, and when we let some of these parameters to tend to infinity or tend to zero, we have to be very careful because certain objects or certain limits might not exist. So we'll first start by analyzing limits and sequences in some detail. So we have a few more minutes, and I'll maybe quickly introduce that point, and then we can continue in the next class. All right. So again, I was being very loose in all of my statements so far, but I always said that. So whenever we're talking about information theory, I always make statements of the form that you can design encoders and decoders such that limit as n tends to infinity of the rate is approximately equal to the capacity, and the limit as n tends to infinity of the probability of error is equal to 0. Right? And we'll try to, instead of using these loose kinds of notation, we'll try to say exactly what each of these terms mean, because after all, for each n, you have a different encoder and a different decoder, right? So an encoder decoder which works for one particular n is not the same as the decoder that you will use for another particular n. They are different. At the same time, I'm saying that the rate is approximately equal to capacity, and the probability of error is vanishing. Okay, so it's extremely important to develop a more formal notation and make precise statements. All right. So since this is going to be a mathematical course, we should, of course, start with some notation, and this is notation that we are used to already. But this is some notation that I will follow in the rest of the course. Some just to avoid any sort of confusion. So typically, rate will be denoted R, probability of errors will be denoted PE, and if I have a random variable, I will typically denote these in uppercase X, Y, Z. If these are deterministic variables, then typically I will use lowercase x, y, or z. So for example, x equal to little x. So the random variable x takes the value equal to x. So for example, you can ask statements like, what is the probability that the random variable x takes values little x? Okay? And I will also use, so some commonly used sets are the set of real numbers, which I will denote as follows. It's this this symbol R. And similarly, the set of integers will be Z. So this is going from minus infinity to infinity. Right? And the set of natural numbers is the set 1, 2, 3, up to infinity. Okay. So this is kind of notation that I will try to stick to. So typically sets will be denoted in this kind of symbols. So if you use LaTeX, then this is what you would call math BB, or sometimes I use calligraphic capital letters to denote sets. Okay, and this is just to be consistent. Okay, and probability mass functions will be typically denoted like Px. So the probability mass function of x will be Px. The probability density function of x, if x is a continuous random variable, it will be Fx. Conditional probabilities will be like Px given y, x given y, and similarly conditional densities will be x given y. Okay, so if required, you should also revisit your basic probability. What is a probability mass function? What is a probability density function? And basics of Bayes rule, and what is conditional probability, and so on. Okay, so you should revisit that by the next class. Okay, so since it's almost 4 p.m., let's call it for the day. We'll continue in the next class. But yeah, if you have any questions, then I'll be happy to take them. Any questions? Okay, so anyway, we'll be sometime later today. We'll send an email as well as confirming whether the time slot works for everyone or if any change is required. Again, if you have not received the Piazza invite, then just send me an email and I'll share it with you. If you have already registered for the course on AIMS, then I will share the Piazza link with you. But if not, and you're just planning to just sit through the course and are not included on Piazza, then just send me an email. If you have any questions, then please feel free to ask them on Piazza. So let's keep this course as interactive as possible so that you can also learn better. Okay, so that's it for the day. I will stop recording. If you have any questions, then you can ask me now or sometime later.